All right, we're going to look at two-dimensional collisions. Again, obviously we're in momentum here. And we know that momentum is a vector. And the important part is that because it's a vector, not only are we going to conserve momentum because there's no external force. Again, as a reminder, we're looking at collisions and explosions. And we're using momentum because energy is typically not conserved. And momentum is conserved because there's no external force. The collision and the explosion, those are just internal forces that cause those things. I understand heat is produced and energy is lost, but momentum is not lost in either a collision or an explosion. And we're going to look in a two-dimensional case because it's a vector. Okay, so what we have here is we have a hockey puck or some shuffleboard puck, M1 moving at V0, hitting an M2. And then after the collision, it's not going to hit it straight on. It's going to glance off. And so M1 is going to deflect up at some V1, at some theta 1 relative to the horizontal. And M2 then is going to go down at some V2, theta 2. And our goal is, if I have information about the original givens, the masses and the velocity, and I also know what happens to M1, so I know that M1 is going to go up at 4 meters per second at 30 degrees, I want to have the ability to find how fast M2 is going down and at what angle it's going down. And the way I'm going to accomplish that is to conserve momentum in both the x-hat and the y-hat directions. Okay, so in the x direction, originally, so really what we're doing is what we always do, we're going to conserve. So the momentum before equals the momentum afterwards. The original x momentum is just m1 v0, nothing else. Afterwards, I have m1 v1 cosine theta 1 plus m2 v2 cosine theta 2. In the y direction, I have no momentum vertically. That's kind of strange, right? That means afterwards, how much vertical momentum can there be? None. Zippo. There wasn't any to begin with, so there can't be anywhere afterwards, which means that m1 v1 sine theta 1 minus because it's down, m2 v2 sine theta 2 has to equal 0, which means those two have to be equal, which makes sense. There's no original vertical momentum before the collision, so then afterwards, m1's momentum up has to equal m12's momentum down. Just like we said, m1's momentum to the right before has to equal both of their momentums to the right afterwards. These are both positive because they're both right. This is up, this is down. They have to be balanced because there's no original momentum. So if you look at what's happening here, I have two variables left. I have v2 and theta 2 left, and I have to solve for them. This is where it gets a little annoying unless you know a little algebra trick. Really, I guess it's a vector trick. So you see how I have v2 here and v2 here? So in theory, I could take this whole equation, or this equation here, and solve it for v2, and then I could chuck it in up here for v2, and then I could only get thetas. But what I also know is I'm looking for the velocity vector. Aren't I really looking for v2 and theta? Don't I actually know that this whole quantity right here, isn't that really just this, which I'm going to call a new variable vx? So instead of two variables, I'm actually just going to replace this thing by vx. And this thing, which I know is v2 sine theta 2, I'm just going to call that vy. And so instead of solving for v2 and theta 2, I'm actually just going to solve for vx and vy, because look what happened. Vx is now the only variable in this equation. Okay, so this is 2 times 10 equals 2 times 4 times cosine of 30 plus 4 Vx. That's amazing. That's easy, right? And then 0 equals 2 times 4 sine 30 minus 4 Vy. Look how much easier this equation now is and this equation is. So I turned them from two equations and two variables to actually separate one variable, one equations. Okay, so now I'm going to type this out. Okay, I didn't have this written down yet. 2 times 10 minus 2 times 4 times cosine 30. And then let's divide by 4. And I'm going to get Vx is equal to 3.27, we'll say, meters per second. And then Vy, I'm going to take 2 times 4 times sine of 30 and divide by 4. And I get 1. So instead of solving for V2 and theta 2, I actually just solved for Vx and Vy. And then from there, I can do the Pythagorean theorem and do 1 squared plus 3.27 squared. I'm going to take a square root and get V2 is equal to 3.42 meters per second. And I can find the angle. Again, it's obviously going to be below the horizontal, so I'm going to take inverse tangent of y over x. So inverse tangent of 1 over 3.27 is going to be 17 degrees. So I now know V2 and theta 2. Okay, so this is a very helpful trick that every now and then, instead of trying to solve some gross system, I can actually just solve for this thing as one quantity and this thing as one quantity, and from those quantities, find V2 and theta 2. Down here, I'll do it the other way. I'll actually show you the substitution. Okay, so that's a collision in 2 dimensions. Conserve it in x, conserve it in y, and then the rest is actually just math. Okay, so now let's look at an explosion. An explosion is the same thing. We have some big box at rest, meaning no momentum in the entire system, and the entire mass is 10 kilograms. And then afterwards, there's an explosion. 2 kilograms is shot straight up at 5 meters per second. 5 kilograms is shot straight to the right at 3 meters per second. You're like, ooh, there must be some third box down here, and it actually must go. I should have asked you instead of labeled it. What direction must it go? Well, it has to go down and left. Why? There's no momentum originally, so there can't be any momentum afterwards. So if you look at the momentum before the collision or explosion and the momentum afterwards, they have to be equal, and they have to be equal in both quantities. There is no x momentum before. I mean, the thing isn't even moving. Afterwards, I have a 5 kilogram box moving to the right at 3 meters per second. And that guy is moving straight up, so it doesn't even count. And then I have some unknown box here of some mass. Wait a second. Do I know its mass? This was 10. There's 2. There's 5. Well, where the other? That must be a leftover 3 kilogram. So I know that I have a 3 kilogram box. It must be moving left. Oh man, but I don't know. So I got that right. That's 3. But I don't know its velocity. We'll call it V3. And I don't know the angle, but I do know it would be some cosine of some angle. Okay? In the y direction, you're like, well, it's nothing moving vertically at the beginning, so there's no momentum vertically. Then I have a 2 kilogram object moving 5 meters per second up, and then I must have some 3 kilogram object moving down at some speed, which is v sine theta. Okay, now I could do the exact same trick I did up here if I wanted to. Okay, I could rewrite v cosine as just vx and v sine as just vy and solve from both. But if I didn't want to do that, I could actually then solve. And so what if I took this equation? This would just be 15 equals 3v. Can I just drop the 3? It's just called a v. Cosine theta. So let's divide by the 3 and get 5. And so then 5 over v. Oh, no, sorry. I want to divide by cosine. Just be easier. 5 divided by cosine equals v. Well, then I can just come down here and say 0 equals 10 minus 3 times v, which is 5 over cosine theta sine theta. So this is just 0 equals 10 minus 15. Sine over cosine is tangent theta. And then, well, I can just add over the 15, divide, so I get 10/15ths, and then I'm going to take inverse tangent of that. And I get an angle of 33.7 degrees, and then my velocity is just 5 divided by cosine of that 37, and I get 6.26. V3 is 6.26 meters per second. And you can check it if you want to make sure that those values actually produce what you need. But whether you have a collision or whether you have an explosion, you have to conserve momentum still. You just have to do it in 1, 2, or 3 dimensions. And these are both 2D collisions. You have your classic hockey puck hitting, and then one goes up and one gets deflected down. Just make sure you're okay with the angles. And then with an explosion, the object could have been, you could have thrown a grenade, and the grenade could have been moving to the right at the beginning, so maybe it had one of this and none of this. But in this case, the object was simply at rest. So there's no momentum before the collision, and so then afterwards, there can't be any momentum, which really just says that all the stuff moving to the right has to have the same momentum as all the stuff moving to the left. All the stuff moving up has to have the same momentum as the stuff moving down, and that's all I'm saying here. This box is moving right, that box must have been moving left. This box is moving up, that box also must have been moving down, which is why I knew I could draw the arrow down and left. Okay, so here's how you do 2D collisions.